I'm going to now turn it over to Emmanuel Candes, who, as you have heard, has worked, has pioneered actually the knock-off filters and is still been working on knock-off filters. But today he's going to talk to us about something new, model-free, robust machine learning predictions, or conformal predictions, as he calls it. So I'm going to turn it over to you. Thank you very much, Emmanuel, for being here.
Thank you very much. I'd like to thank the organizers, and especially John Leone and you, Edo, for inviting us. I enjoyed the talk by Junyu very much. I think it's fantastic work, and it's extremely important. I've learned a lot from Jun when I was a student. Jun was a professor at Stanford when I was a beginning graduate student, and I've learned a lot. I'm still learning a lot from Jun. I'm teaching a Markov chain class where I use this fantastic book to stimulate students. So it's a pleasure to be in a panel with Jun.
Thank you very much.
Today, I'll talk about reliable and recent progress in predictive inference. Next slide. And, this was machine learning 15 years ago. The goal was to predict movie ratings. And I think in hindsight, we can say this, which is whether we got these predictions right or wrong, it did not matter. Next slide. But fast forward to today, we're using machine learning tools in extremely sensitive applications. For instance, for facial recognitions and drivers, and you've heard the problems associated with this. Next slide. I'm not sure if you know about this, but probably you do. People use machine learning tools to assist judges in US courts to make decisions. For example, there are companies who sell products, essentially criminal risk assessment scores, to help judges make decisions about who should get paroled, who should get bailed. And it's very hard for me to think about a more critical application of machine learning, a more sensitive application of machine learning, as it directly impacts our lives. And so, next slide, please. Of course, AI has a lot of promise. We are being sold that AI will improve medicine, will improve healthcare, and people use deep learning for medical diagnostics. And I think in automated healthcare, I think we should learn when we need to pass control to a human doctors when the diagnostic of a network, the confidence of the diagnostic of a network is low. But how do we know that a deep learning architecture, which is very opaque, is well calibrated? How do we know that its confidence is low? And so I think it becomes extremely important as we deploy machine learning to work on more and more sensitive applications that impact our lives directly, to be able to assess uncertainty a bit better and to understand when is it that a deep learning or a gradient boosted machine has low confidence in its prediction. And so as a toy example, we can imagine that we are a university like Stanford or Harvard, and they want to recruit students, and they gather a lot of features about each applicant, and they're going to try to perhaps offload some of the decision to a machine learning system that would predict how well this candidate will do at Stanford. And perhaps a deep learning architecture will spit out a score of 3.62. But then how much confidence do I have in this prediction? And the way I would like to think about this in this lecture is through predictive intervals. So this is very easy to follow lecture, I think. The way we're going to think about this is we need reliable systems. We need to understand that when the cost of a wrong decision may be extremely high. And so traditionally in statistics, we like to produce confidence intervals. So here we're not going to talk about confidence intervals about parameters. We're going to talk about predictive intervals, about future observations. And so what I would like to see more often in the way data scientists and AI researchers communicate the outcome of their research is in the form of these predictive intervals. So I would like to have a prescription, which is that it's not enough to give me a point estimate. You have to give me a range. And I want this range C of X, that is a predicted range of labels. For example, in the case of my student, it would be the predicted range of a GPA after 2 years at Harvard, let's say. And I would like this range to be accurate 90% of the time. That's a prescription. And I think we all agree that as the consequences of our decision impact people's lives, this is extremely important. Now, why do we not see this more often? Next slide. I think we don't see this more often because we are way past simple regressions for which we have learned simple formulas to actually construct these predictive intervals. We use methods that are quite opaque and are very powerful, but it's not easy interpretable. And there is a whole lot of research that I will not talk about in this lecture that shows that somehow that this method can be really badly calibrated. But I think one of the reasons we do not see predictive intervals is that we use very fancy algorithms that by all means we should almost treat as black boxes. Next slide. Yet we'll see something a bit bizarre in this talk, which is that it is possible to construct predictive intervals that are valid no matter what the distribution of the data is, no matter what black box you're using. And this is work that was done with Yaniv Romano and Evan Patterson last year. Next slide. Now, this is something concrete. You'll see a method that is concrete. And I was pleased to see that actually it was picked up by the Washington Post by the fantastic work of John Cherian and Lenny Bronner. Lenny Bronner is a data scientist at the Post. John Cherian is a Stanford student working for the Washington Post. And they use a method that I'll present to actually project results on election night. I'll say more at the end of the talk about what they've done. But I've been informed, and of course, during the night of the election, I watched the projection from the Post with my heart beating, and I was informed by the news desk that the model worked very well. Next slide, please. So, what are these prediction intervals? So, in abstractly, what we have is we have a bunch of training data, as is common in machine learning, and we have a test point. So, the features Xi's in the case of my applicants might be, which high school you went to, what were your high school grades, your ACT scores, your level of physical fitness, extracurricular activities, information about your parents, siblings, whatever. And Y is a sort of a quantitative measure of how you'll do if Harvard, say, were to admit you in its prestigious university. So what we'll do is the goal is to construct a predictive interval, a set C of xn plus 1 that contains a true label 90% of the time. And we don't want to make any assumption about the distribution of xy. We don't want to make assumption about the sample size. We want this to work always because the stakes are high. So in plain language, we want to say that based on the candidate's high school identifier, GPA, ACT scores, and everything I can have measured about an applicant, I would like to predict that the GPA range will be between 3.4 and 3.8. And I want this prediction to be correct 90 or 95% of the time or whatever. Next slide. Okay, so I just want to start with, suppose you had solved the problem. So what does it mean to have solved the problem? It means that suppose you know the distribution of y given x. Okay, so if you knew the distribution of y given x, you can see that, I don't know if you see, do you see my mouse? Probably not, right? You see it? No. So you can see that at every value of x, you would know the distribution of the response given x. And therefore, you could compute the lower quantile and the higher quantile of this conditional distribution. Next slide. And you could connect them to get, for each value of x, a very valid predicted range because you know the distribution of y given x. So I gave away the problem to you, and you compute the quantiles of the conditional distribution of y given x, and then you connect them. Next slide. But this is too easy. I don't know what is the distribution of x and y. All I have is this. What am I supposed to do? So we're going to do two things. Next slide. We're going to connect two areas of statistics. One is quantile regression, and this is a fantastic paper. So if my talk can be anything, it's just an encouragement for people who listen to me to read this wonderful paper by Roger Conker and Gilbert Bassett from 1978 about quantile regression. Next slide. So, okay, so I see the math did not come out too well, but on the PowerPoint translation, but I hope you can try to see what this is. So we're going to try to formulate the learning problem as as a regression problem. And so instead of using your usual squared loss, I'm going to use a loss which is called the spin-ball loss that you see on the right. And on the right, you see something that looks like the absolute value function, except that the slope may not be the same. And this is a loss that function, when you use your neural net or your gradient boosted machine with a loss function like this, will actually try to find the conditional quantiles in your data instead of the mean. So if we use the squared loss, then of course we're fitting the regression function. But if we should fit one of these losses, we're going to try to find the conditional quantiles in your data. So I'm suggesting that we're going to use this very fancy algorithm that we've talked about before, neural nets, gradient boosted machines, not with the squared loss, but with this loss to actually try to find the quantiles in the data. And so what you could do is we try to do this. This is a quantiles fitted by some method, and then we fit the lower quantile and upper quantile, and we hope that this will approximate the true quantiles. Now, is this valid? Next slide. And it is not valid at all. In fact, for those of you who have experience with neural nets, and we certainly fit a lot of neural nets at Stanford, you know, neural nets might actually go to zero training error, which means that the two quantiles will be the same roughly. And so you can imagine that your out-of-sample performance will be a disaster. In this case, because we were trying to be careful, it's not a disaster. It's about 66% coverage. You want 90, you got 66. Obviously, your quantiles estimate are too optimistic. Next slide. So what we're going to do is we're going to take this first impulse and we're going to wrap around it. And we're going to build a wrapper around the, a neural net quantile estimate machine to actually make it calibrated and make it valid. And as we'll see, the method we propose will work no matter the sample size, no matter the dimensionality of the data, no matter the black box you use, no matter the distribution of the data. Next slide. So how's this going to work? So there are many versions of this. I'm going to present the simplest version, and then whomever is interested, Ido was kind enough to collect references, and so there are lots of variations on what you'll see in the references that are in the library. So you give me a data, I'm going to split it in a proper training set and a calibration set. Okay, so the proper training set is on the left, it's in black, the calibration set is on the right. It's a bit like what June was saying, it's a bit of a data splitting step. You don't have to do it, but it's simpler if I present it this way. Next slide. On the first set, you actually run your quantile regression estimate. But now we know that it's not going to work. So we're going to see how well it does on the calibration set. And we're going to score how well this does on the calibration set by scoring each individual point. Next slide. So we're going to score individual points, and a point will receive a positive score or negative score, depending on whether it's within your prediction band or outside of your prediction band. So you're going to have a positive score if you're outside of the prediction band, and a negative score if you're inside the prediction band. All right, next slide. And how these scores are constructed, it's very, very easy. So if you're outside, I'm going to look at the nearest boundary, and that's your score. If you're inside, I'm also looking at the nearest boundary, but I put a negative sign. Okay, so let's say that we have 300 points in the calibration set. Therefore, we have 300 scores, and these are signed distance to the nearest boundary. Extremely simple. So now I have 300 numbers, and what do? I take the 90th percentile of these 300 numbers. So I'm looking at the 270th largest values of these percentiles. And I'm going to return as my prediction band whatever I fitted with my neural nets, but adjusted by this Q. I'm going to subtract and add Q. Now let's understand what this is doing a little bit. So suppose by some miracles, the neural net was actually fitting very good quantiles to start with. Then 10% of the point would be outside, 90% would be inside, and therefore the 90th percentile would be roughly 0, in which case I would not touch the great job that the neural net has done. But suppose the neural net, as is often the case, is too optimistic it's too confident about its predictive power. The thing will be too narrow, and so there would be more than 10% of the points outside. And so therefore, when I look at the quantiles of this course, it will be positive. And so what that would mean is I would actually enlarge the width of my prediction band. If you're, on the other hand, a bit like June and myself, you're a bit conservative because you were well trained, maybe you start with quantiles, and that's kind of an interesting point. You start with quantiles that are a bit too conservative. You want 90%, you get 95%, in which case your value Q would actually be negative, and you would actually shrink that. It says, no, Emmanuel, you followed yourself, you're too conservative. You don't need to be that conservative. You would actually shrink your estimate. Next slide. And when we use this procedure on the same data set, it's too good to be true. I want 90%, I get 90.09%. So this is quite remarkable. Next slide. Is this an accident? No, it's a theorem. And the theorem is that you can prove that this method, which is very, very simple, as you can see, achieves 90% coverage, almost exactly. That is, it's a theorem that the coverage of your predictive interval is at least 90%. That is, your predictive interval will contain the true response 90% of the time, and no more than 90%. And again, it applies always. Next slide, please. Now, what I'm not saying is that this is building up on the work of Vladimir Vovk, who is a person I admire, is working in England, at Imperial College, I think. And so what we're doing is we're marrying quantile regression with ideals for conformal inference. Next slide, please. I think Vovk got a lot of things right, almost everything right, but maybe not the last part. And so what Vovk was advocating is to fit, and again, the math did not come out right on the translation, but basically you fit a neural net, or you fit a learning rule by minimizing the squared loss, you compute the residuals, and then you build the prediction band by actually looking at the prediction at a new test point, plus or minus the quantiles of the residuals. And the reason I think it's not exactly the right answer is that, as you can see, your prediction interval has constant widths, right? So it has a center, which of course depends on where you are. It depends on your regression function, but the width is constant. And that's not capturing the heteroscedasticity that we have in the data. This is going to be made extremely precise on the next slide, please. On this plot, where we have a very heteroscedastic data set, where essentially the conditional variance of y given x changes as a function of x. And you see on the left, you see the Vovk approach, which is essentially fitting a prediction interval of constant widths with the CQR method that I'm advocating, which you see that somehow the width of your interval depends enormously of where you are in space. As a result, it's a theorem that both methods achieve 90% marginal coverage, which is what you see empirically. But the reason, like what we adaptive means that the method we have has much shorter length, so it has more informative intervals. Next slide, please. So the right picture is essentially a length of the interval produced by these two methods as a function of x. And so you can see the blue curve is our method, the CQR method. The red curve is Vovk methods. Vovk method produces intervals with constant widths where we are highly adaptive as to y in x. Now, there is something which is very interesting here, which is also check the conditional coverage as a function of x. And the blue curve, which we see on the left, achieves almost a lot of conditional coverage, no matter what the value of x is. But the Vovk method doesn't. And sometimes it undercovers, sometimes it overcovers. And you can see that in finance application, if we can go back one or two slides. Go back one slide. Yeah. One more slide. Yeah. So if we go back one more slide, I think one of the problem is, suppose that the data is heteroscedastic and you actually build confidence prediction interval based on the size of the residuals, the quantiles of the residual. suppose you're in finance, because I think that's one of the themes of the conference. Suppose you're in finance, and you have periods where you have high volatility, period where you have low volatility. I think what the Vovk method will do is will tend to undercover in the high volatility because the response is more spread, and it will overcover in the periods where the volatility is low. So as a function of volatility, you'd either undercover or overcover, while the method we propose should be far more adaptive to the level of volatility because it's what you fit when you fit your quantile regression. So let's go back 2 slides. Go up 2 slides. Forward 2 slides. Yeah. One more slide. Yeah, so we actually did a lot of data analysis. We used these methods, which are implemented, which I'll give you links to website where you can actually download Python and R packages to actually predict utilization of medical services. This is one of the data set we looked at. We have lots of covariates, age, marital status, race, poverty status, and so on. And the goal is to predict healthcare system utilization, for example, as measured by the number of visits to a doctor's office or hospital, and so on. It's a high-dimensional data set with 140 features and 16,000 subjects. Next slide. We use one of this extremely sophisticated method of neural net regression with a pinball loss. We use this TQR method. And so it's a theorem that both Vovk's method and our method achieves marginal coverage. This is what you see on the left. In terms of conditional coverage, we do better. And in terms of lengths, we do better. So we produce intervals that are more adaptive. They're shorter. They have better conditional coverage. And they have exact marginal coverage. Next slide. So this is if you're interested in healthcare, but we looked at Facebook data. We looked at a lot of data from science, and you can look at the paper. And so what we found is that this method was helpful, would outperform traditional methods in 10 out of 11 regression data sets that we actually have looked at. All right. There is an extension, next slide, please, to discrete labels. And how much time do I have left, Edo?
About 5 minutes.
Okay, so I have 5 minutes. So maybe this is instead of discussing these extensions to discrete labels, maybe I can just tell the audience that, of course, there are lots of problems where the response variable is categorical. What kind of objects do I have in front of a car if I'm interested in a self-driving car? And you would like to be able to also return short predictive sets in classification problems. And we have extensions of the method that you've seen to deal with categorical variables. In the interest of time, I will skip this slide and the next. So next slide, next slide, next slide. This works well. And I will just wrap up to go back to election night. So next slide, please. Yes. So again, I want to emphasize that this is not really my work. This is the work of John Chirian and Lenny Bronner. I think I mentioned before that John Chirian is a student at Stanford and Lenny Bronner is a data scientist working at the Washington Post. Next slide. So these are the kind of information you could see displayed on the Washington Post website. And so, the Washington Post, and this is the Washington Post, November 4th at 11:50 at night. And so this was the state of Pennsylvania, which, as you know, was a very contended state. And so the Washington Post was issuing predictions based on the model. Next slide, please. And so what you can see from the next slide is very early on, the Washington Post was able to predict, if you look at the left panel, that Biden would eventually win Pennsylvania. And so they had a very good way of actually displaying prediction intervals by using a very delicate color scheme. And they also were able to break their predictions in terms of the kind of county that you were. And so, so this is the kind of information that the Washington Post displayed running the method you've seen. Next slide. This is a few days later, November 7th at 8:30 a.m. Of course, the prediction became tighter because we had more data. Next slide. And, now quite a bit of confidence that Biden would be ahead when the count is finished. And so, as I said before, the model worked quite well. So next slide, please. So, okay. So I had prepared some slides, but they were translated, and so somehow we don't see them very well. But basically, the way, just to give you a sense of what was on this slide. So the way the Washington Post looked at this thing was that counties are going to start reporting, right? And so for each county, we have a bunch of county features, demographic features, whether it's an urban or not urban, and so on. And so the Washington Post was interested in predicting 3 types of outcome. One is the voter turnout in 2020. And to do this, they defined a regression variable, which was the voter turnout in 2020 minus the voter turnout in 2016. And then they were interested in the number of Republican or Democratic votes, which we're going to write RI20 or DI20. So this is the number of Republican votes in county number I in 2020. And of course, the number of Democratic votes in the county number I in 2020. And as a regression variable, they used the fraction, the difference in the rate for which you vote for Republicans and Democrats between 2020 and 2016. And now counties start to report. So you see variables. So you see the data from a few counties, and you have missing counties. And you're going to use the method you've seen to actually predict to actually build up confidence prediction interval for the counties that have not yet reported. Now, there's one thing that should make you worry. Next slide, please. It is, are counties being reported, are we drawing counties out of an urn? And no, we are not, because the counties actually do not appear in random order. You know that maybe some counties with some characteristic report earlier than others, so the data is not exactly exchanging. And that's where the thing breaks up a bit. But, I'm not going to go through the details of what was done at the Post to actually deal with this issue. Because you had access to previous elections, you could see by playing the movie of the counties in the order in which counties show up, you could adjust the confidence level to make sure that all through the night and the ensuing days, you maintain coverage. So the only assumption we make here in this talk is that the data are shown to you in a sort of a random order. It's not exactly the case, but the Washington Post came up with a very clever way to adjust the inference to deal with the ordering based on previous elections. Next slide. So if you're interested in this, there's a website and code. I think June said it nicely. It's important to be transparent and reproducible. And so people can download and reproduce what we've done. Next slide. And I think my time is up. So I showed you a method to basically get reliable predictive intervals. I think it's extremely important as we deploy machine learning in very sensitive applications. The election is one of these sensitive applications. It's important to get it right. I listed quite a few references. If people are interested in the theory and the work of Vladimir Voff, there's his book, Algorithmic Learning in a Random World, that I recommend everybody take a look. It has changed a bit my life. And so with this, I'll pass it on to you, Pedro.
Thank you very much, Emmanuel. Very cool method. Again, one more innovative, very cool method. Like June, I'm a big fan of your work, as you know, and for everyone, Emmanuel is very understated and very modest, but he only combined a couple of ideas that existed out there, but clearly, he knew which 2 ideas to combine and exactly how to combine them to fix the issues and apply them to a very important problem. So, well done. Thank you for sharing your work with us. And Vovk reference is listed, by the way, on our content library. So please, with the link. So please take a look. Thank you again.